Thank you very much for the invitation. It's, of course, an honor and a pleasure to be speaking at this conference. Before I start, I have a painful announcement to make concerning the proof of the conservativity. So about a month ago, when I was writing down the last bit of that proof, I realized that a statement, which is the theorem 8.3.10 of the paper about conservativity, which I thought was an extension, which somehow looks very much like another theorem of that paper, which I know how to prove, which is theorem 2.1. Turned out that one was much harder than that one, and so this was about a month ago, and since then I've been trying somehow to find a proof of that, and somehow not succeeding. So, which means that somehow, as for today, the thing that I will be speaking about somehow will be conditional on the validity of this statement. So even if I write theorem, you should keep in mind that this might not be a theorem in the future, since it might depend on this, which might be wrong. All right. So this is said. The theorem that I want to discuss today is the following. So remember, this is conditional on that. So it says the following. So we start with K, a field of characteristic 0. And the theorem says that there exists, so it's about an existence of a map. So there exists a map of algebras in DM. So this is Voevodsky's categories of motives, and I usually work with coefficient in K, and you will see that this is indeed a natural thing to do. And so the map has the following shape. It's a map from a homotopy limit of a diagram which is indexed by the category of simplices. So it's a cosimplicial object. It's a Hodge construction on some object omega that I will explain in a moment, and that should goes to something also which depends on omega, which is a truncation of omega. So the main theorem is just about the existence of such a map in Voevodsky's categories. So let me explain a little bit the notation here. So omega is just this is the object in the MK that represents algebraic theorem cohomology. So in the sense that it's characterized by a universal property, which is the following. So whenever you have a motive and you look at morphism between this motive and omega, then this is a group which is isomorphic to the theorem cohomology of the motive. So maybe I should write it. So the H0 theorem of any motive is the same as morphism between M and this object. And this characterizes this object somehow uniquely. Or, yeah. Okay. So this is omega, and let me. So the other notation are as follows. So this C Hodge dot. So this is a construction which makes sense for any algebra. So if I have an algebra A, this is a cosimplicial algebra, which has the following shape. So it starts with A, then it is A tensor A, and so on. And so the map in this direction are just given by inclusion of the unit. So, and the map in this direction are given by multiplication of A. And this is, of course, just the dual construction of what we have seen, I think 2 days ago, in the proof of Voevodsky of the Milnor conjecture. So we saw this object chi, which played an important role, and this is really just, if you think, it's just a dual construction of that object here. All right. So and then this is a homotopy limit. So I will not recall what is the homotopy limit. Is somehow something. I mean, you can think about it as you have a double complex and you pass to the total complex in some sense. So it's a rather easy to define construction, but it's actually quite hard to compute. And the remaining notation is that thing here. So this tau bigger than 0. This is a truncation. So this is truncation for the so-called homotopy T structure. On the M. So the M is expected to have a very nice T structure called the motivic T structure, but we don't have this. We have instead something different, which somehow is a bit mysterious, since it doesn't really have an analog in any classical context. And this is called the homotopy T structure, and somehow it comes from the construction of the M. And this is a truncation for this T structure. So a good way to think about this object is as being the connective cover of omega. So if omega would be it's a spectrum in some sense, and this is just the connective cover of the spectrum. Right. So this is the statement. So let me maybe explain why such a statement is of interest. So here are some remarks. So the first remark is that the statement has to do with so-called conservativity. In fact, so this main theorem implies the conservativity of the theorem realization. And of course, by comparison theorem, it's also implying this for any classical realization. So let me let me sketch the argument, and in a special case. So here's maybe a proof. I said in a special case, namely the case of a Chow motive. So if M, let's take M to be a Chow motive. Such that the ramp cohomology is vanishing, has no ramp cohomology. And so the goal is to show that we want to show that M is itself 0. Okay, so how can we do this, assuming this main theorem? Take some place. Okay, so we argue as follows. So the condition that the ramp cohomology of M is 0 implies the following: that if you take M and you tensor it with object that represents the ramp cohomology, it's 0 as a motive. Okay, so from the vanishing of this group, you get the vanishing of this object in the M. And this is actually very simple. So this implication, in fact, more generally for any M, let me take general object n in the M. So in fact, n tensor omega happens to be isomorphic to the theorem homology of n tensor with omega. And this is just an instance of the Kunet formula for theorem cohomology. So if M has no cohomology, it also has no homology, and therefore we get this. And this, of course, implies that more generally, the M tensor with this Čech construction on omega is 0 also as a co-simplicial motive. And of course, it's true that the homotopy limit of this is 0. But now, since M is a Chow motive, it has a strong dual, and therefore tensoring with M is like taking internal hom from M dual to something, and therefore tensoring with M commute with homotopy limit. So I could just put this outside. Right, so this is an important step which has to do with the fact that M has a strong dual. And now, if this is true, then I can use the morphism, which is not, oh, it's still there. So this morphism then, and the vanishing of this object, so this implies, now I'm using the main theorem, this implies that the morphism from M to M tensored with tau bigger than 0 of omega is 0. So this map is 0 as a map in the M. Okay, so, and so let me continue. So we are now almost done. So in showing that M is 0, which one?
From the vanishing of the tensor product to the trivial
From the vanishing of the tensor product?
No, from that bottom line.
Sorry. From here?
Yeah.
To?
To the right.
To here. Oh, yeah. So this is because we have, you see, we had a map. So we have a map to M tensor tau bigger than 0 omega, which is just taking the map of the main theorem and tensoring with M. All right, so the main theorem give me a map from the homotopy limit to this truncation. I tensor with M, and of course there is a map from M to here, which is induced by the unit. So now this guy here is 0. This means that the composition in particular will be 0. And this is what I'm saying here. Okay? Right, so now we know that we have a map which is 0, and we want to deduce from this that M is itself 0. So for this, we remark the following. So so if I take, so I do it for M. So the group of morphism between M and M tensor, this truncation, happen to have a nice interpretation. In fact, it happens to be simply morphism as Chow motives from M to M, but mod out by the by algebraic equivalence. And this, I mean, it's actually, yeah, so this is actually just a reformulation of, so in this equality, there is, essentially, there is only the block formula. So the block formula tell me that, in fact, for any, so if I take two Chow motives, I have this equality. So morphism from M to N tensor something, tensor this guy is just morphism, algebraic cycles between M and N modulo algebraic equivalence. If there's interest, I can say more about this, but I think this is quite, really quite easy. All right, so once we have this, now we see the map that we had here. So let me call it star. So this map, which I know to be 0, so star, which is equal to 0, is also equal to the class of the diagonal of M in here. So the conclusion of all this is that the identity of M is 0 up to algebraic equivalence. And we know, and this is the theorem of Voevodsky and Voisin that we heard about yesterday, that if a self-correspondence is 0 in up to algebraic equivalence, then it is nilpotent. Right? So by Voisin and Voevodsky, nilpotence, this implies that delta M is nilpotent and hence it is 0, as we want. Okay, so this is essentially the link between the statement of the main theorem and the conservativity. All right, so any question about this? Okay, so let me make a couple of more remarks about the statement, or about consequences of the main theorem. So this argument I just sketched can be improved. So maybe mark. So this argument can be improved using, so as I was somehow, as I learned from Bondarco, this can be improved to show that, in fact, the functor from the MGM k to dbk is conservative. So not only conservativity for Chow motive, but even for all mixed motives which are geometric. Also another consequence of the statement is, so was also mentioned in the talk of Voisin yesterday, is a nilpotence conjecture. But I should maybe here make it precise. It's not the smash nilpotent. It's really the nilpotence of composition. So namely that if you have a self-correspondence of a Chow motive which is 0 in homology or cohomology, it has to be nilpotent. And this is actually not a direct consequence of the main theorem, but somehow of a refined version of it. So let me explain this maybe. So just very quickly, so one needs a refinement of the main theorem, which has essentially the same proof as the one I stated, and of course, again, depends on the validity of this statement 8.3.10. And the refinement is, say, the following. In fact, there exists a map from, so more generally, so from the homotopy limit of M tensored with Chech omega to M tensored with tau bigger than 0. Now this seems very similar to the statement of the main theorem, except that, I mean, and of course, if M, somehow the whole point is that you have M inside the homotopy limit. If M was outside, then this will be just the same statement as before. And so I'm telling you that you can put M inside, but this is actually not true in general. So under some condition, so for M, essentially, or for M cohomological up to twist. So there's a condition that is necessary for this to be reasonable. And so this condition is that cohomological up to twist. I will not define what is cohomological up to twist, but let me just say that if you take a Chow motive and the self-correspondence and you look at this, let me squeeze this there. So the point is that, so to get the Nilpotence conjecture, what you do, you have, let's call it N, with the self-correspondence, a Chow motive, and you know that gamma is acting by 0 on cohomology. So what you can do, you can look at this sequence, right? And you can take the co-limit of this. And if you know what is the definition of cohomological up to twist, then you will see that this guy is cohomological up to twist. And therefore, you can put it somehow in this refined statement and get the conclusion you want, namely that gamma is nilpotent using somehow the same ideas as here. Okay, so in the remaining of the talk, I will try to say a few words about the proof of this main theorem. Okay, so there will be two parts, so maybe part one. The proof itself somehow can be naturally split in two parts. So part one consists, so this is, which is also somehow a large part of the whole proof. This somehow consists in finding or constructing and then computing a replacement of omega. So let me say what I mean by this. So omega is an object of dm. So maybe an explanation. So omega is an object of dm. And it comes with a canonical model in some sense. So dm is a homotopy category. So it's obtained by, so it's like a derived category. It's obtained by inverting maps. And somehow objects in dm, you can a priori represent them in different ways. But omega somehow comes naturally as a particular object, which is very nice and very simple. And by the way, the object of this category are called T spectra. So they're of course called also motives, but somehow when I speak about a T spectrum, I think about it as an object in the model category that give me this triangular category. So there is a T spectrum, canonical T spectrum, which somehow represent this omega. It is very simple to write down. It's essentially given by the de Rham complex. And so what the part one of the proof is about is somehow to find a different model to omega, and you can think about it as but by a model I mean this talk. This will be the new model. This will be the replacement. So this is something that comes with a map to omega, but this is a map in in the model category. That give rise to this. And in the model category, this is, I mean, these two objects looks very different in the model category. But and this is one of the point of this part is in fact that this map will be an isomorphism here. So it's an equivalence. It's a motivic equivalence. And one good way to think about this is as follows. So you think about this omega as a space, and this is like somehow some kind of a cofibrant replacement of your space. So it could be much bigger than your space, but it has somehow the same homotopy type. All right, so somehow part one consists in finding an interesting such object, which somehow will have some features that are important for part two, that I will maybe try to explain later. So let me just give you some idea where this guy comes from. And so to do this, I will simply list some of the ingredients that are used in constructing this object, and try to tell you how they are useful in finding this replacement. Okay, so what are the ingredients that are used? Okay, so one of the ingredients is the so-called foliated topology. This is one ingredient. Second one is so-called P1 delta localization. Then what do I need? Yeah, motivic Verdi reality, and a lot of computation. So somehow these are the what you need to use somehow to get these. So I'll explain each of these ingredients. So I'll explain how do they enter in this construction. All right. So I will not recall what is the foliated topology, but let me briefly say the following. So the foliated topology is designed so that Poincaré lemma holds. And so as a consequence of this, let me put this here. As a consequence of this, we can think about the algebraic drum cohomology. So algebraic drum cohomology becomes a sheaf cohomology. And so by sheaf cohomology, I mean the cohomology of a simple sheaf, in particular of a sheaf in degree 0, exactly like the case for example, singular cohomology. So we can think about the algebraic drum cohomology, which is usually defined as a Zariski cohomology of some complicated complex, as the cohomology for a complicated topology, but of a single simple sheaf. And this is obviously somehow interesting for the problem because I'm trying to understand somehow the ramp cohomology. So this gives a perspective about the ramp cohomology that happens to be useful. All right, so this is the first ingredient. Let me go on. Okay, so we now speak about the second ingredient, namely the P1 delta localization, or maybe rather I should say P1 delta invariance. So this somehow came from the following very simple observation. So so first let me say what is P1 delta. So P1 delta is just a notation for P1 made discrete, and more precisely, so this is P1, the usual P1, but endowed with a discrete foliation. Which means that the leaves of this foliation, they have dimension 0. Right, so the observation somehow behind this notion is that if you look at the theorem cohomology of P1 made discrete, then it's not hard to imagine what this should be. This should be simply the Zariski cohomology of P1 with values not in the round complex, but simply in the sheaf O. And of course, everybody knows that this is K star. K is here. So as a conclusion, we see that somehow P1 delta is contractible. So somehow the slogan is that P1 delta is contractible for the drum cohomology. Okay, and now, I mean, since the work of Voevodsky and more of Voevodsky, we somehow there is a natural thing to do whenever we encounter such a phenomenon is to look more generally if there are other interesting theory which has the same feature, which are somehow invariant with respect to this space, which is not really an interval in the technical sense of Voevodsky, but still it makes sense to speak about theories which are invariant with respect to this object. And in fact, I don't know any other example, I think, a natural example, of course, that has this property. But what you can do is that whenever you have an object, you can force it to become invariant with respect to this kind of line. Right, so this is what is P1 localization. So P1 delta localization. This is the process of forcing P1 invariance, P1 delta invariance. And this is something really familiar for people who works in motive, I think, at least motive in the sense of Voevodsky. So, for instance, if I have A1 instead of P1 delta, this procedure is essentially by a theorem. It's essentially given by the Sustin-Voevodsky construction. So maybe let me write it here. So just to make an analogy, so the A1 localization, this is just essentially you take the Sustin-Voevodsky complex and you apply it to your object. Okay. If you want me to say what it is, I can, of course, but maybe it's not necessary. Okay. So. All right, so what can we do with this P1 localization?
Is there a similar explicit construction that gives you the localization function?
So there exists indeed an explicit construction, but it's really way more complicated than the one we are used to. You can find an explicit thing. But it's really, and I will not be able to write it down today. It exists. I can say a few things about it, but and it's something which will be useful for me, but I cannot really write it down on the blackboard. All right, so yeah, so why do we care about this notion? It's because of the following fact, which at least for me came as a surprise, is that one can recover this object that represents the rank cohomology from its effective cover. So this is another notion of cover. And it's not the connective cover, it's really the effective cover, which actually has a simple form. It's an infinite suspension spectrum on the de Rham complex. So from its effective form, by applying P1 delta localization. And here, just to be precise, so this is this should be computed in the foliated topology. Which, by the way, I write as FT.
There's no analog in DM.
There is no analog of DM of what? No, this has no analog in DM, yes. I mean, it has, yeah, you cannot speak about this object in DM, yeah.
But by recovery, you mean by passing, you have to also pass the Fourier topology when you recover.
Right, so I mean, what I'm really saying here is the following. So you have the natural map here, right? And this guy here is P1 delta log invariant, as I explained. I mean, essentially because of this computation, but it's also it has descent for the foliated topology. So you impose descent here and P1 delta localization, and you get this via this map. Right. Oh, I still have 15 minutes, or am I? Oh, 20 minutes. Okay, I should maybe hurry up a bit. So, all right. So the upshot of this is that somehow you from this one get a model of omega, which is constructed out of things of the following form. Our internal home, some product of P1 delta, this guy. Oops. So, and here I have to put the foliated topology. So this is why is that? Because as Mark suggested, there exists an explicit form of this P1 delta localization, which is somehow similar to the Voevodsky construction, and therefore it will involve taking product of P1 delta and computing internal homes between them and your space. Okay, so if you have A1 instead of P1 here, these are the objects that somehow are used to construct the Voevodsky complex. Okay, so this is just, I mean, basically, if you have a variety here, you are looking at the value of your theory on P1 delta cross X, and this gives you a new theory in some sense, and then out of this you construct. You can construct the localization. Now comes this the Verdier. So this, I mentioned the Motivic Verdier duality, or maybe Grothendieck-Verdier duality, this is somehow, this enters in here somehow to replace RFT by a version of the etale topology, which is somehow a crucial step later. Okay, so I don't have time to say more about part 1, so now let me maybe quickly go to part 2. All right, so, all right, part 2. So once we have done, so the outcome of part 1 is to give me some kind of cofibrant replacement, which I denoted by Z of the object that I'm interested in. And I have to say that this, so after some computation, starting from here, this guy can be really described purely algebraically without mentioning foliation anymore. So we have this object, and then the next step would be to try to understand if we can say something more about the Čech complex of Z instead of omega, and hopefully enough things that somehow enable us to prove the main theorem. And somehow this is the construction of the map that is in the main theorem. So this is somehow part 2. And let me again here maybe just say what are the ingredients instead of really going into the details. So what are the ingredients? So one main ingredient here is a Hodge theory. And by Hodge theory, I really mean many things in Hodge theory, in fact. And at the end, somehow, I end up using a lot of Saito's theory of mixed Hodge modules. This is really so this is a big somehow external ingredient, and then somehow some ingredients which are closer to the subject, namely facts about motivic homology. Really simple fact, some things like purity and so on. All right, so I maybe tried the remaining of the talk somehow to explain why Hodge theory is relevant to this problem. So it turns out that before we are able to construct the map that we want, we really need to simplify or to make some important computation about this Čech resolution, about this Čech construction. So we need really to simplify. Right? So somehow in part 1 we made the problem somehow look much more complicated by introducing this gadget Z, and now somehow we need to simplify things somehow in order to be able to construct this map. So simplifying the Čech complex, and this is of course up to homotopy. Right, so we will somehow try to find maybe a subcomplex, really a sub-Koseplichak object, which then we can show that it gives the same limit at the end. And to do this, so we need to construct. So we need to construct homotopies. In the usual sense, really homotopies in the sense that if you have a morphism of complexes and you are constructing homotopies really in the usual sense. And these homotopies somehow they are given to us somehow. These will be given through Hodge theory. So just to, maybe I explain a baby case somehow just to give you an idea how Hodge theory can give us homotopies. Here's a simple baby case of a situation where Hodge theory somehow does what we want. So first, remark that if you have an algebra A and any tensor categories, and if A has a unit, so it has a point, a co-unit. So assume that your algebra has a point, then it's really an easy exercise to show that that one mapping to this is a homotopy equivalence, or maybe I should say cohomotopy equivalence. I don't know, but it's homotopy equivalence. And induces an isomorphism on the homotopy limit. And this is the reason for this is, again, some explicit homotopies, which are very simple. So I just write them. So what you do, you look at the augmented cosimplicial object, Četř, and so on. And you look at the identity between these two things. Identities, and you use your point to construct the homotopies. Okay, so this is a fairly simple construction. Now, and it has nothing to do with Hodge theory, of course. But now let's see. In our situation, we don't really have obvious points. Let's see. So if you would try to somehow to mimic this argument in the situation that you are considering, we see that we have some problems. So let me first so let's see. Here's a fact which somehow rules out such an argument, is that omega has no point. This is very clear and very easy to understand. I mean, if you have a point, you mean that means that you have you have a map from the RAM cohomology to motivic cohomology, which is a section to the class cyclic class map, and this is of course very far from reality. So this has no point, and therefore there is no way to do such a thing. But it turns out that that the effective cover has a point. That's okay, and it has a point because of Hodge theory. So because, or one way to construct a point is to use Hodge theory, and this is because, in fact, so this is the RAM complex. So this is just the RAM complex, so over K. So it turns out that there is an isomorphism between this guy and the weight graded so the object is fitted to the weight filtration. It's the gradient for the weight filtration of omega. And now let me just write it in the M effective. So this is the variant where we don't invert the Tate motive, and where the objects are simpler, are just given by complexes of presheaves. And of course, this does not make sense on the level of the complex itself. It's of course, this is somehow really, and this is non-canonical. There's such a thing which exists because of the theory of weight, because somehow weight are essentially, to some extent, are given or equivalent to a graduation. And since we have this, we can project to the degree 0, which happen to be the unit object. And show that this guy has a point. And somehow the argument essentially consists in trying to find an alternative way to somehow to try to mimic this kind of arguments in a more complicated situation. And you see the reason why I was happy with the formula P1 delta localization of this is, of course, because on this gadget here we can run this argument, but not on this here. So somehow, yeah, the big part of the proof is to try to somehow use this fact and try to construct homotopies. Okay, so I still have 5 minutes, so maybe I continue. So I could continue a little bit with this argument, to try to explain a bit more about these homotopies, or I could stop here also. So I don't know. Yeah. Okay, so the point now, so the reason why this replacement happens to be better suited for what I want to do is because it turns out that one has a filtration. So on this or an integer. And it's an exhaustive filtration, so it means that you can write z as a co-limit of this thing, where each of these gadgets somehow they can be described. They can be described. So using object of motivic type. Namely, and more precisely, using some variation of mixed source structures living on basis of dimension, let's say, smaller than n. So I did not tell you how you should think about this z, but somehow z will be a big object, and so it will be some kind of a big co-limit, and the different, so the pieces that somehow that enter in constituting this z, they can be associated, for example, by taking a global section and so on, to some variation of mixed source structure, some big diagram of variation of mixed source structure. And what one do essentially is that one bounds somehow the dimension that are allowed to enter, and this gives this filtration. And it turns out that this also has no point, but it somehow it will have a point up to nilpotence of order n in some sense. So let me try to write this down. So by a lot, I don't know, there will be a big diagram of varieties. I mean, and on each variety there will be a variation of mixed source structure, and then we take the cohomology of this local system, and we get groups, and we put them all together to construct the values of this object. And it's really, these are really, I don't know, big diagrams, so it doesn't make sense to write them down now. But so it's not like you take 3 of them, or it's really. There will be always of the form. You see, we have maps. So there will be of motivic origin. So there will be of the form Ri f lower star of 1. But for many choices of these of maps. So and plus maybe logarithmic sheaves, some logarithmic sheaves that also enter. So there are rather yes, it's a simple thing, but there are many of them, and it's hard somehow to write down a useful formula for them. All right, so yeah, so if we bound the base, the dimension of the basis, then something interesting happens, namely that one can really salvage this argument. So and really show that the homotopy limit of the Čech thing of so for a single n, yeah, it's computable. There will be some homotopies, and the homotopies will be again given from the fact that we have this variation of mixed Hodge structure. But somehow the theory of weight does not work as in the case of a point, because we have many bases and we have to compare the bases. And so what we end up showing is that there will be no points, but somehow there will be a point maybe after tensoring with some big algebra, which is essentially an algebra of continuous function with value in the real, let's say, or maybe complex. So you see this C infinity function with value. And see, this is a complex. This is a pre-sheaf on smooth varieties. And if you tensor somehow this with this, then you'll be able to write down a point. And then there is a way to get rid of this without really destroying the argument. And this is because the dimensions are bounded. Yeah, and somehow the rest of the computation comes from the fact that you want somehow to get rid of this n, which is not an easy thing, since, as I told you, z is a co-limit of the Fn, and co-limit do not really commute with limits, so an argument has to be found, and this is where somehow I use some specific properties of motivic cohomology to be able to do this. Okay, so I think I stop here. Thank you.